You know, with every breath you take, you're inhaling millions of invisible particles. Now, most of them are totally harmless, but a few have the power to do everything from just giving you the sniffles to, well, shutting down the entire planet. Today, we're diving deep into the world of human respiratory viruses.
But let's kick things off with a question you've probably asked yourself before. Why is it that you have to get a new flu shot every single fall, but that measles vaccine you got as a kid, that's good for life? It's a really good question, and in this explainer, we are going to get to the bottom of it.
So, to solve this mystery, first, we've got to understand the enemy. And believe me, not all respiratory viruses are created equal. They exist on this huge spectrum of severity, so let's start by just mapping out the landscape. Okay, think of this like a lineup of the usual suspects. Over on the left, you've got your everyday troublemakers, rhinovirus, adenovirus, the guys that cause most common colds. In the middle, things get a bit more serious. We're talking about respiratory syncytial virus, or RSV, and your seasonal influenza A and B. And then you've got the ones with global potential. That's where you see influenza A again, alongside those now infamous coronaviruses, like SARS-CoV-2, MERS-CoV, and the original SARS-CoV.
Yeah, that first column, that's the stuff we're all familiar with. The common cold isn't just one virus. It's usually a rhinovirus, but it can also be one of the less famous seasonal coronaviruses. You know, like OC43, NL63, 229E, and HKU1. They'll give you a runny nose, maybe a sore throat, but your immune system kicks them out pretty fast.
But then you get something like RSV. For most of us, it just feels like a really bad cold. But for babies and the elderly, it can be incredibly dangerous. Get this, RSV is responsible for about 20% of all childhood hospitalizations in the winter. It's a serious reminder that even a seasonal bug can be a huge threat to the most vulnerable. All right, now that we have our map of the viral world, let's zoom in on that one familiar enemy, the flu. Every single year, a new wave hits, and every year, we have to fight it with a new vaccine. So, why the constant battle?
The whole answer boils down to this one key concept: antigenic drift. The influenza virus is basically a master of disguise. And the most important part of that disguise is a protein on its surface called hemagglutinin. As the virus makes copies of itself, it makes these tiny little errors or mutations in the genes for that protein. It's kind of like a spy who changes their disguise piece by piece. One week, it's a new hat. The next week, different glasses. Each change is super small on its own, but over time, they add up. Eventually, our immune system security cameras, our antibodies, they just don't recognize the spy anymore. And boom, the virus waltzes right past our defenses. And this constant process, this antigenic drift, is the direct answer to our question from the beginning. It's why you can get the flu over and over again. And it is exactly why the vaccine has to be updated almost every year. It turns into this high-stakes guessing game for scientists at the World Health Organization who have to predict which new disguise the virus is going to be wearing next season. So how do we fight back? Well, we have two main tools in our arsenal. First, there's the classic flu shot, the inactivated vaccine. Think of it like showing your immune system a mugshot of the virus. It can't hurt you, but it teaches your body what the bad guy looks like. The other option is the nasal spray, a live attenuated vaccine. This is more like a training mission with a weakened version of the virus designed to build up your defenses right at the entry point, your nose and throat.
But what happens when the threat isn't just a virus with a new disguise? What if it's a completely new character, one our immune systems have never, ever seen before? Well, that's what happens when a virus jumps from an animal to a person.
The scientific term for this is zoonosis, and it's the origin story for some of our most dangerous viruses. For many coronaviruses, for example, the natural home, or reservoir, is bats. And bats are kind of the perfect viral incubator. They live in these huge, dense colonies where viruses can spread like wildfire, and their immune systems are so unique that they can carry tons of viruses without ever getting sick.
And we have seen this play out again and again. In 2002, we had the first SARS-CoV, which jumped from bats to people, probably through civet cats. 10 years later, MERS-CoV showed up, linked to bats and camels. And then, of course, 2019 brought us SARS-CoV-2. You can see the pattern here, right? It's pretty clear. So why did the first SARS outbreak get contained while SARS-CoV-2 exploded into a pandemic? Well, the critical difference was timing. With the original SARS, people were most contagious after they started showing symptoms like a fever or a cough. That gave public health officials a chance to find sick people and isolate them. But with SARS-CoV-2, people were spreading it before they even knew they were sick, and that made containment almost impossible.
But there's one final, really dramatic twist to this story. A completely different way viruses can evolve that can create a global pandemic almost overnight.
Let's compare. We've talked about antigenic drift. That's the slow, gradual disguise change that gives us seasonal flu. But then there's antigenic shift. This is not a disguise change. This is a complete identity swap. It is an abrupt, massive genetic shakeup that creates a virus so new that basically nobody on Earth has any immunity to it.
So how on earth does that happen? Well, the flu virus's genetic code is split into 8 different segments. Now imagine an animal. Pigs are a famous example. They're often called a mixing vessel, gets infected with a human flu virus and a bird flu virus at the exact same time. Inside one of its cells, those genetic segments can get all mixed up and reshuffled. This process is called reassortment, and it can spit out a brand new hybrid virus with a totally novel combination of genes.
And this isn't some crazy theory. It's written in our history books. The devastating 1918 pandemic was an H1N1 virus that probably jumped straight from birds. But the 1957 and 1968 pandemics, H2N2 and H3N2, those were classic reassortment events. And even more recently, the 2009 swine flu was another H1N1 that jumped to us from pigs.
Which brings us to today. You've probably been hearing about the H5N1 bird flu. Now, to be clear, the current risk to people is extremely low. But the fact that it has started spreading in new types of mammals, like dairy cattle, is exactly the kind of thing that makes scientists pay very close attention. It's a real-time reminder that these viruses are always out there, probing, testing new hosts.
So here we are. We live in a world with viruses that can slowly drift, forcing us into that annual race with the flu, and others that can suddenly shift, creating a brand new threat in the blink of an eye. Both of these forces mean the viral world is never, ever standing still. It's always changing, always challenging us. Which of course leaves us with the biggest question of all. Knowing everything we know now, are we ready for whatever comes next?